So this morning now we have Miehlbradt, and he has taken on a very interesting venture of teaching CPU architecture to high school students. So this will be very, very interesting. Please go ahead.
Cool. Cool. All right. Thank you very much for coming. So I'm going to be talking about my attempts to teach CPU architecture to high school students and kind of the benefits, the troubles I ran into, and how I went through that. So first of all, I am a Linux kernel developer at IBM, but I'm not talking about anything related to that. Instead, I'm going to talk about some work I did a couple years ago where I was one of the coordinators for the Canberra Computer Science Enrichment program. I'll go briefly into what that program actually does in a second. And I also put up there I'm a former tutor, or some universities call them TAs, at ANU. And the reason I mention that is that's about the sum total of my teaching experience. So I'm not coming here from any sort of place of professional pedagogy. I don't really know what I'm talking about professionally. So hopefully this is an interesting reflection from someone who really didn't know what they were doing and kind of figured it out along the way. So very briefly, the Canberra Computer Science Enrichment program was run by the CoLab, which is a joint ANU ASD organization. They do a whole bunch of things, as you can probably imagine by those two organizations working together. But one of the goals was to grow Australia's future STEM pool. And one of the methods by doing that is they funded this program, the Canberra Computer Science Enrichment program, where we got a bunch of high school students in from around Canberra, and we talked to them and worked with them on various computer science topics. So the aim of the program was to encourage students to develop an interest in computer science, perhaps as a tertiary pathway, to kind of help them become more aware of the role of computing in their lives broadly, encourage them to become active users rather than just passive consumers of technology and of computers. And if this by any chance got a few Canberra students into ANU degrees and into the future ASD hiring pool, that's also an added benefit. Definitely not what they were trying to do there. So the topics we presented were really varied. We got a lot of ANU academics to come in and talk about their research area. And myself and the other coordinator, Dirk Pattinson, we also delivered a number of sessions. And so, we had a really broad mandate to talk about really whatever we wanted to, as long as it was computing oriented. And the final point I want to make about this program is the method by which we selected students, where we sent out a bunch of requests for nominations to various math and computing teachers in high school and asked them to nominate a couple students who they thought would benefit from this program. And then we took that and selected from that list. So we had this really good group of really bright students who were really engaged and had some prior interest in computer science. Maybe they didn't realize it at the time. They maybe didn't think it was computer science. It was just computers. But that's the kind of the group of students we had. And finally, we ran 1.5-hour sessions every Friday during the school term. So the question comes to me as to when I chose to do a couple sessions on this topic, why did I actually choose this? The first reason was, like many of the other sessions I delivered, I was already kind of teaching it and thinking about it in my role as a tutor at ANU. So a lot of the material is actually based on a second-year computer architecture course that I was TAing for at ANU. And I just took the material and kind of adapted that, which, to start with, is a pretty ambitious goal, I think, to take second-year university-level computer science and teach it to 15 to 18-year-olds who don't really have the benefit of perhaps a year or two of formal computer science education. And I really wanted to give them an understanding of how, the electrical devices actually compute stuff. What is going on in the wires of your computer when, you run a program or, do any sort of other action. And I wanted to really hide from them, hide as little as possible. So kind of not really have any black boxes or just trust me on this. It'll work. I really wanted to make sure that they were kind of engaged with every part of the system that they were building. I was not 100% successful in that final point, but hopefully you'll see that later. So I first started with an architecture. So for those who aren't really well versed in computer architecture, you have something called an ISA. That's instruction set architecture, and it's basically just a specification that says, these are the things the processor can do. This is kind of how it does it. These are the operational semantics. This is how it's encoded. This is what a programmer or a compiler writer can assume about the processor. So I needed a specification to actually get the students in. And so I kind of came up with these 4 requirements. They need to be A, Turing complete, because I don't think it's particularly interesting if it's not. Simple enough to implement in 4 sessions. The 4 sessions was a somewhat arbitrary decision. That was about half a school term, and I felt that was like a good amount of time to spend on a single topic. You need to be able to write like simple but still non-trivial programs. I used a Fibonacci sequence as a benchmark here, saying if you can easily compute Fibonacci numbers, that's probably fine. And it needs to be easy to hand assemble because I wanted to get students actually taking the assembly they write and then converting it to the ones and zeros or the hexadecimal and poking it into the memory of their little simulation. So I had these 3 ideas. Existing ISAs, far too complicated. They are hundreds, if not thousands of pages long. They're not easy to hand assemble. You can write good programs in them. That's probably the only benefit. But yeah, so that was kind of right out. There do exist some teaching ISAs, like at ANU we had an ISA that we were teaching. Again, though, these were a bit too complex because they spend a semester implementing these, and I had about 6 hours spread across 4 weeks. So again, not really there. And that kind of left me to creating my own ISA, which was the best approach. I just created something really simple. Yeah, so I've actually got over here, this was the document I provided them. So at the end, I'll have links to all of this if you're interested. But 8 registers, 8 instructions. For those who have seen ISA before, there's some pretty glaring omissions as to things you would normally expect. But this is a very restricted set of instructions that is very easy to hand assemble. For example, aligning things to 4 bits, it's very easy to convert between binary representation and hexadecimal representation in 4-bit chunks. So all the opcodes of the instruction are 4 bits long. All the registers are aligned to 4 bits in the instruction, those sort of things. And yeah, I've omitted some really key features like call instructions to enable function calls. There's 1 jump if not 0 instruction. No ability to kind of read where the program's at. But I think these limitations actually sparked a lot of interesting discussion, and I'll loop back to that later. So the other thing that I started off with was I needed a digital logic simulator for students to actually implement this thing in. And I landed on this program called Digital. It is a digital logic simulator, as the name would suggest, developed by this gentleman named Helmut Niemann, and it's open source, of course. The one thing I dislike about this is its name. It's very, very hard to Google. If you just Google digital, you will not find it, so you have to remember the creator's name and prepend that if you ever want to find this piece of software. And if I jump over here, this is pretty much what it looks like. You can kind of introduce logic gates. I can add some input pieces. if I line these up nicely, you know, you can connect them up. And now if I add an output here, and you know, it lets you run it, and then you can play with these as you interact with these, and you've got, you know, like a simple AND gate. It's got this really nice, rich set of components built in that you can use in your designs. It's very, very useful. And it turned out this piece of software, I think, was one of the great successes of the sessions. It really enabled students to, you know, get in, and you can see what each individual wire is doing. You can add, you know, inputs that you can toggle live. It has like a functionality for like I think a clock that you can run in real time. I think the creator has a reference CPU he implemented, and you can run it at about, I think, 120 kilohertz. So it's reasonably performant. You know, you can actually run reasonable programs on it. I think there's even like a VGA peripheral that you can that it models, and you can create little like animations on the screen. Cool. I have a screenshot just in case the demo fails. But yeah, there's a little bit more complicated. One thing that is here interesting to note is all these wires are actually 16 bits wide, so it's not just a single logic value. It lets you bundle wires together, so you can really easily interact with not just like individual 1 zeros, but like whole values on a bus, which makes things a lot less tedious. Yeah. Cool. But yeah, I think these mentioned, it's like a really great playground to just mess around with introductory digital logic. It's got a whole bunch of useful features that I don't even touch in my sessions. You can write input-output tests. It's even got like a scripting language where you can programmatically generate circuits. The one feature that is really important, though, is the ability to create nested subcircuits. So for example, we've got on the, which side for you guys, the left is a half adder, and then once you create that circuit, you can actually drag it into another circuit, and the inputs and outputs that you set in the smaller circuit become these little boxes in the larger circuit that you can actually interact with, and you've got this really nice encapsulation that lets you reuse components and not just have to rebuild everything from scratch every time you want to do something. And it can also, it even has some like transistor components, and it properly models 3-value logic with high, low, and undefined, if that's the level that things go at. This is not the level I went down to. Takes a little bit too much time, I think, but it is possible. So I want to talk now kind of about how what the sessions actually consist of, and how I went from Boolean logic all the way to a working processor. So we started with basic combinatorial logic. You know, we would give the students a truth table and get them to create a circuit that implemented the truth table. I didn't really use any rigorous approach for anybody who's done any sort of like electrical engineering or digital logic. There's our formal ways of translating truth tables into logical expressions or circuits. I didn't do any of that. May have been a mistake, especially as we progress to the end and things get a bit more complex. But this was pretty much done because I did not have the time to express these things in detail. But because I had full control of the design of the instruction set architecture, I could design things in such a way that I could avoid the most gnarly bits of logic that they may encounter, and have it so that, you know, everything works out to be fairly simple to just look at the truth table and identify. And kind of once we created these like smaller circuits, we would you know, be able to import them and reuse them in larger, more complex designs. So as an example, we've got a truth table and then the half adder. The students kind of were already familiar because, fortunately, we had a previous session on Boolean logic, so students knew what logical operators were, and they knew what truth tables were, so I could point them at this and they would go, oh yes, that cout is an AND operator. Oh yes, S is an XOR. And then they could actually see those operations in digital logic in digital. And so yeah, the only thing I had to introduce there was the pictorial representation, nothing more. So that was a bit of a benefit, and again, saved me a whole bunch of time. We then kind of, upgraded the logical thing from, half adders now full adder, so you can actually have your carry in and your carry out. So you can chain a whole bunch of these together, like you're doing, arithmetic when you do your columns and you carry over the next one. It can actually take that carry in. So this is kind of somewhere where, not using a formal approach is a bit of a hindrance, because it's pretty challenging to just look at the truth table and say, oh yes, that's what, these are the logic gates I should use to combine it. So kind of instead I took a more intuition-based approach where I was saying, okay, think of it as you're just adding 3 bits together, but because addition is a binary operator that's commutative and associative, you can just squish them together in pairs, and it doesn't really matter. And you only need this one extra bit of logic to deal with if either one or both of them produces a carry that you then pass on to the next chain of adders. And kind of at this stage, we had a ripple carry adder, where you can just, then this becomes its own encapsulation. You create a bunch of those, link them all together, and students have created a circuit that can add 2 16-bit numbers together. And we managed to get through this in the first session, which I was pretty happy with. And once you've done that, we also had another exercise, which I haven't created slides for, where we created a multiplexer to select between 2 different inputs. And then, actually, if I go back a couple slides, that's all you really need to understand what's going on in here. We've got the adder circuit, which we created, so students kind of understood what was going on when you're adding 2 numbers together. You have your bitwise OR, your bitwise AND, and your NOT. And then you just have a 2-bit selector that picks which operation that you want done. And so conveying this to students that, well, what's really going on is all the operations are happening in parallel, and then you just choose which one you want and just ignore the rest, was really made concrete when you have a visual representation like this, and you can actually poke numbers into each of the values A and B and choose your operation and get different results. Cool. The next topic gets a little bit more complex. So combinatorial logic is not much good without any ability to store a state. And this is kind of, I think, where my first flop was when I said, I'm going to try and give you hidden, no BS explanations of why things work. It's really hard to justify why this particular pair of coupled NAND gates produces the behavior you want. And in fact, in digital, if you try slightly different configurations that should theoretically produce an SR latch, sometimes it doesn't terminate, but that's only because it does so many iterations that it never settles into it never arrives at the steady state. It thinks that you've created a circuit with infinite fluctuations, and that is really hard to implement. So this is kind of the first place I said, trust me, bro, this is an SR latch. I gave them the circuit they can play with, but didn't really explain to them how they could derive this, from their own. And even when I was teaching, the university course, this is something that we spent a whole week on just by itself, trying to get students to understand this concept. But once we had the SR latch, it was actually a bit easier, because then we can say, cool, the SR latch does the storing of the state, and we can upgrade to a D latch where I can just say, when we're enable the latch, it just passes through whatever to the output. When we disable it, it saves the state. And you can set up a truth table, and we did this as a group for the students for the combinatorial part. And so we're kind of back on the ground of, okay, we're understanding what's going on. This is, not exactly how it's implemented in transistors. You don't really need this kind of intermediate SR latch. You can express it much more with much fewer components. But from an explanation perspective, or from a pedagogical perspective, I think that was probably fine. But once again, I fell on my face and had to do another Trust Me Bro when I had to explain why we needed a synchronizing clock so that all registers updated at the same time. This was a bit easier because if you give them this circuit and you attach Q to D and you put some logic in the middle and you click enable, this basically just acts as a wire, and you can create these fluctuations where it never settles into a final state, and the digital will complain at you. But I couldn't really motivate as to, again, why this particular set of pairs of D latches would create this synchronous behavior, where if you now connected Q back to D with some logic in the middle, why that would now work. The best I could do was, analogies with airlocks, where, you never have both gates open at once so things can just flow through. You always kind of have one side closed over the other so that it kind of locks things in place and never stops. Like, you never had this kind of free-flowing circuit. It's a flawed analogy, and something that I really struggled conveying to students. But it worked in the moment. But this was kind of the final building block we needed to actually progress back to building, core CPU components. So we combined, put 16 of these D flip-flops in parallel to create a 16-bit register that stores now a 16-bit value. And then we can add a whole bunch of control signals and explain and show that to students. This is where the diagrams get, the circuit diagrams get too big to display on a single slide. So I've cut off the bottom of this one, but it just is the rest of the 8 registers that are expected. But once again, I think I violated my rule of, this should be kind of an intuitive, you should understand intuitively as to why you need different parts. So I just kind of told them from on high, okay, we're going to create 2 read ports, so you can read 2 values at the same time. That's the 2 multiplexers here on the right, without really justifying that. And in hindsight, that's something I could have really easily corrected. That's more of a flaw in the way I delivered it rather than thinking about it, because you can point out, hey, you need to read 2 registers at the same time to do an add operation because you need 2 inputs. And then, of course, you have the right side where you're only writing 1 register at a time. That kind of backward multiplexer, it's a demultiplexer, and that was the one we didn't design kind of as a group. We didn't break it down and look inside it, just because it's a bit tedious. I did suggest students, if they were interested, they could go home and try doing it themselves. I don't think any did, but I like to believe. But once we had the ALU to do the computation and the register file to store results, we actually could get somewhere in something that starts to resemble a processor and get students kind of really excited at this point, where you can connect your 2 reads to your 2 inputs for your ALU, loop back the result to the right, and then have all these inputs that you can manually toggle. So students can, in RF read cell 1 and RF read cell 2, they can put which register they want to read from, and which register they want to write to, choose what operation they want, and then actually toggle the clock, which is its own separate component there, and it does the thing. And so students got really excited here, because this is kind of the first point where you could actually start doing what looks like computation in kind of a way that might be recognizable. So registers kind of are analogous to variables, and then your ALUs, your operations on them. But students get very quickly bored of toggling things. Also one other thing I forgot to mention, digital has a really great feature which lets you just poke values into registers directly. So even though we started with nothing in the registers and our ALU has no ability to produce values from nothing, we could still get students to poke values in without having to design other components. So this is kind of our minimum viable CPU is what I called it in the session. And it provokes some really interesting motivating questions like how do we get values into the register to begin with? Like where do we actually get these values from that we're actually operating on? And yeah, posing these kind of thought-provoking questions right at the end of the session was a great way to get students to go home and think about it and then come back next week having forgotten what they thought about in the hour just after the session. But at this point, I think we need to start introducing some way to actually store instructions. And we added this memory component. That's this little white box here. The white signifies that it's a built-in component, whereas the tan is a custom component that we designed. And it's a bit small, and yeah, I think we're starting to get to the stage where the figures on the diagram are not really readable by the people in the back, but it's not really important anyway, because I'll talk through it. So we gave them this RAM component, which has 2 read ports. The reasons for that are so that we can both read the instruction and read any potential data from the memory if we have a memory manipulating instruction. We can do that all in one cycle to reduce complexity. And once we had memory, Digital has this nice kind of interface which you can pop up, and it basically is just a grid view of the memory, like if you were to like hex dump it, but then you can go and poke the values directly. So students really get this intuitive understanding that it's just a list of instructions, and this input that we're producing from the PC is now just an index into that list of instructions to say, this is the next one. And we had all the components. Students know what an adder is. They can create a register. So they can create a register that just increments every clock cycle to increment through instructions. And we kind of get to this point where we're still kind of manually poking the control lines, but we've got this extraneous line coming off to the side there, and that's where we actually read the instruction from and then do something with it. So at this point, we have all these control signals, and we have this instruction that's coming out of the memory, and I get to tell the students we are back to our old good friend combinational logic, and we just have to turn this 16-bit value into all the signals that you've been toggling on and off manually every single time. I don't have an image of that just because I forgot to store it as an isolated component, so it's a little bit complex, kind of nestled in with everything else. But that was kind of where we got. There was a little bit of difficulty there because, like I said, I designed the ISA. I can make it so that the logic for the control lines is never particularly complicated. So, for example, you can always take the upper 4 bits and use that to decide what operation is being done. The ALU operations are nicely set up so that the 2 bits always, the same 2 bits always go through to the ALU, so you don't even need to add any logic in between. You just take out those 2 bits and wire them in directly. All the registers, all the operand registers are always in the same place. Again, don't really need to add any logic there. The only kind of challenging pieces, or comparatively challenging pieces of logic, come when they have to choose which output they have to detect if they're doing a memory operation or an ALU operation. And so, yeah, once we had that, we were pretty much almost there. We just had to add all the other bits that actually finalize implementing the specification. So if I jump back quickly to here, we have this 0 flag, which I used for my conditional jump. So we just added an extra register to track whether the last ALU operation produced a 0 result. Again, just combinational logic to determine that. So students were fairly happy doing that on their own. We had the put instruction, which I've kind of neglected, and that's our way of just sticking an immediate value into a register to actually, get somewhere. And then we had this jump not zero, which was where we kind of had, again, a little bit more complexity in the control unit. And students struggled a bit here, just with the idea that now we're not just depending on the instruction, whether we update this program counter control signal, but we actually have to look at this flag as well and introduce this additional input to our control unit to look at the flag. But yeah, once we do that, students produce something that looks like this, very messy, kind of but a very high level overview of what all the pieces wired together looks like. And we got pretty much all the students had their own version, maybe not arranged exactly like this, but they got their own CPU. And this is in digital, kind of a fully functioning CPU that implements the specification. You can poke values, you can put a list of instructions into memory, hit the clock run button, and it'll execute those. And so, yeah, we got students to write some assembly programs. So we kind of started, fairly straightforward, adding two numbers together. We got them to multiply numbers, so introducing the jump not zero to create loops. And then, like I said, the Fibonacci number was my kind of benchmark for how expressive I wanted the ISA to be. So we got students to write a program that generates up to the nth Fibonacci number. And I think most students, got there. I'll talk about that most qualifier in a little bit. But yes, this kind of started to generate some interesting discussion once we got to this point. Students started getting very frustrated about having these seemingly arbitrary 8 instructions that I chose for them. They wanted to do things like, can I write a function? How do I kind of modularize my code? If I wanted to multiply a number over here in my program and over here in my program, do I have to just duplicate this entire block and figure everything out? Because we only have a 0 flag, we can't do things like, or we can't easily do things. Of course, it's Turing complete, so you could theoretically do anything. You can't easily do things like greater than and less than. Again, you have to have loops decrementing each number until one of them reaches 0, and then you can tell which one is 0, and then you get there. So I think I had 1 or 2 students that did write this out. Kudos to them. It was tedious. And then we also have really notable glaring exceptions. There is no subtract instruction. I decided to just totally omit subtraction from this, pretty much exclusively because I didn't have the time to explain 2's complement representation, which is how computers typically represent negative binary numbers. This is going to be on this is on my GitHub. You can feel free to have a look. I can make it bigger for the people in the back. So yeah, so I mean you can do the typical. I was always taught in my discrete math toggle +1. So you can toggle all the bits with a naught and then add 1 by poking a 1 into a register and then adding it to create negative numbers. So you can, instead of going a minus b, you go a plus negative b. And again, we had some students get there. Most were just really frustrated when they wanted to decrement loops, that they had to go about this kind of whole thing and poke this magical value 1, 1, 1, 1, 1 into their registers to decrement value. But yes, but the struggles here did prompt some really interesting discussions about what makes a good instruction set. And ultimately, kind of that was my goal with these sessions, is to prompt interesting discussions. How expressive is it? Do you make it for your compiler writers versus how difficult for your hardware implementers? So we were on the extreme end of easy for hardware implementers with these students, but we could kind of get them to see how moving more towards the compiler writers would make it more friendly by writing assembly instructions. So what I actually did was I produced, because we did a session after these, specifically on writing programs in assembly, where I introduced kind of an extended. So this is fully backwards compatible, but I introduced some things like a subtract instructions. I added a return instruction, a call instruction, so that you could actually have some more complex semantics. And I didn't get the students to design and implement this. We actually ended up doing this about a term later. Again, somewhat arbitrary decision of let's revisit this topic. But I gave the students a digital model that they could write programs and run them and then see what they got. But yeah, so designing the ISA and creating 2 versions of the ISA really helped to get students to understand, what is going on from the perspective of a hardware designer or a compiler writer trying to actually write tools to generate these programs that could be run in instructions. So that was kind of the overall session. I'd want to talk now about the hurdles specifically, the things that I did not do well. And this is probably the point where anybody who actually does have a background in education is going to go, duh, you should have seen this coming. But these were fun new discoveries for me, and I felt like they were insightful enough to share. So the first one was I personally found it really difficult to just not lecture at the students. I like the sound of my own voice. I like talking about computer science. So it's really easy to just talk. And my background in teaching at ANU was either giving presentation, lecture-y style things, or helping students in self-directed labs where they already knew the content and were kind of working through exercises themselves, but much more self-directed. But these sessions kind of have to fall somewhere in the middle of that, where you're teaching them the content, but also giving them the chance to kind of explore and be self-directed in what they create. So I think that's something there that maybe I would improve my personal teaching and also the pacing of the sessions. But yes, the second point was I don't think I accounted for this perceived complexity. So I keep mentioning, it's just this simple combinatorial logic. I've mentioned this many times for designing all these things. But especially when we got to the control unit, and students were dealing with, I think, 8 or 10 different outputs, even though each one is its own isolated component, because they had them all in the document at the same time, it's really easy to look at and go, whoa, this is way too much. It's really hard to kind of parse out all this information. And leaving enough time for students to kind of get their head around that was a bit of a challenge. And then, of course, there were a few places where I kind of had to go, trust me, and had a few black boxes with the sequential logic and the register file, and the sign extension to do the jump not zero instruction. I didn't really have a good way of explaining in about 5 minutes why duplicating the most significant bit out to as wide as you need actually creates these backward jumps. So there were a few things there I maybe would like to improve. Like I said, I delivered this, I think, in 2022. So it's been a while. I would like to deliver it again. The enrichment program's currently not running because of some stuff in Colab I'm not privy to. But I would definitely spread it over more sessions. 4 sessions, in hindsight, incredibly ambitious to take students from nothing, well, Boolean algebra, to a CPU in 6 hours over 4 weeks, while they have a whole bunch of other stuff. At ANU at least, students are spending roughly 10 hours per week per subject. So this is, less than one week of university teaching time equivalent. In order to kind of improve this, black boxy feeling, I think the exercises maybe should have been some should have been a bit more guided, especially towards the end to mitigate this kind of perceived complexity issue, while kind of maybe taking the exercises at the front half of the sessions, kind of the creating the half adder and the full adder, and just letting students explore a bit more and discover things on their own, rather than just kind of saying, here's the truth table, let's go from there. Kind of saying, here's a very big problem, let's think about and discuss this for 5 minutes before actually jumping really into it. And giving them some more time just to kind of play with digital. We kind of jumped in very quickly. The controls sometimes are a little bit unintuitive, especially with a trackpad. Most students were on a laptop with a trackpad, which is a bit challenging. And then reordering some of the topics. So for example, bringing the control unit before memory. So instead of students kind of poking things around with memory, they would just put an instruction into a control unit and have things come out, and then introduce the concept of a sequence of instructions with a program counter. This would be, yeah, something I would probably like to experiment with if I deliver this session again. So wrapping everything up, overall, I think students were incredibly happy. Several students cited this as their favorite set of sessions. I don't think there were too many that didn't like them. They don't tend to tell you if they don't like stuff, as is the nature of being an authority figure. But it was a really good topic that I think a lot of students didn't know that they wanted. Computer architecture is not really a visible thing when students start, kind of their first forays into computer science. They kind of come across Python and web stuff, and these days they'll come across LLMs and AI pretty quickly. But computer architecture is kind of this hidden gem that students don't realize is there and really interesting to delve into. And it prompts a lot of really interesting discussions, then launching off about compilers, the role of an operating system on top of that, so on and so forth. And it also really helped improve my teaching skills. I got the chance to have a captive audience of 15 high school students and really just figure things out. And yeah, I think it's helped my development, be able to explain complex topics to people who don't have as much exposure. And yeah, I think if you get the opportunity to teach things at this level, take it. It's great. But altogether, thank you very much. Also, sorry, slides aren't up yet. They will be up at lunch. But also links to the session materials and the software will be in the slides if you want.
Usual thing.
Thank you. Do you feel that students had the context of how this relates to production architecture of what machine had been?
Not at the start. That is something that I kind of brought up towards the end. Obviously, I chose a single cycle implementation because it's very simple. It maps very much one-to-one to the instruction set architecture. But yeah, this was one of the things that was interesting discussion point, saying, hey, this is an idealized model. It's not actually how things work. Real processors are chopping up instructions to several parts, dynamically reordering them, and then executing them in the best way they can. And one of the things I did is in the final set of slides I did for this session is I just threw up a whole bunch of terms on screen saying, hey, if you're interested in this further, here are some things you can Google. Or come talk to me about after the session or whatever. But yeah, so that was kind of one of those launching off points that I talked about.
Have you considered using some game to lure the students in, improve their motivation? For example, I know a game, and I'm a very big fan of the game called Turing Complete, which covers everything you talked, and it's super addictive. And I guess a student with enough motivation will take 10 hours and finish the level almost to the level you mentioned. So yeah, I'm interested if you are using the same game to improve the motivation.
Yeah, so I do know of Turing Complete specifically, and a few others like it. I discovered Turing Complete after delivering these sessions, so I didn't use it at the time. I think, yeah, using games is a great way to do it. One of the, I think, really strong points of this program is that the way we select students, we ask for nominations from math and computing teachers, so we get students who are already really bright and invested and kind of self-driven. So I think in this context, the context of this enrichment program, maybe not necessary, but delivering this to maybe a wider group of students, I think absolutely, yeah, that would be a great way to kind of engage them if they don't necessarily already have that interest.
Anyone else?
Yeah.
Have you tried building human logic circuits? So using, saying to someone, you are an OR gate, and when someone touches one shoulder or the other shoulder, you touch the shoulder of the person in front, and so forth.
I haven't tried.
Because that gets,
Yeah.
that gets the head around what being a logic gate is.
Yeah. If I did this again, I think that would be a really fun thing to try. The main flaw with that is just the time it takes to organize the students into, a cohesive mass to do the thing. So, again, going back to if I made this a 6 or like maybe a whole term topic, we could like really dive much more deeply into the kind of get students that kind of physical intuitive understanding. But yeah, that's a really great point.
Thank you, Nicholas. And I'm sure it would have felt like quite a thankless task at times, but ultimately it's really, really important for our business and our community with having people like you actually taking that time and putting that effort into teaching the kids. So that's really important. Thank you very much.
Thank you.
And here's a little gift from Everything Open for you so that you can proudly show that you have been one of our speakers.
Thank you very much.